Hi, I'm Antonio Sala, and in this video we are going to discuss multi-output stochastic processes. And well, this will be a first video in which we'll discuss an intuitive motivation and some examples and how they are described. But the actual formula and code will be left for subsequent videos. So what do we mean with a stochastic process with two outputs? Well, stochastic processes are, an object whose realizations are random functions, time series, whatever. So we may consider, let's say, that I am studying climate data. So I have some registers of some meteorological stations at different latitudes, say equator, say 80 degrees north, series of them. And then I may have some data from temperature readings at a given date or the mean in a year or whatever. So I have some temperature samples at different stations in different latitudes. Then if I have some prior on how smooth these temperatures are, I can use that prior to, let's say, interpolate these temperatures in a statistical sense. So I may have an expected value, mean, and a confidence interval, which of course will be narrower, close to my actual measurements, and it will expand when I am far away from measurement. So, well, I can have this thing, and this stochastic process will be defined, and the computations will root on knowing the covariance between temperature at some latitude x1 and then some other latitude x2, usually with a given covariance kernel, kappa t, x1, x2, say exponential of minus x1 minus x2 squared divided by 7, or this kind of things, or matern or whatever. Well, that's unimportant now. We'll put concrete examples in numerical simulations. The thing is that this would be a temperature analysis as usual. But okay, we can imagine that my meteorological stations also have humidity sensors. So I have another record of data with humidity measurements, and maybe I have a prior, a model or whatever, maybe, adjusted with this or past data or whatever, in which I estimate the covariance between humidity at different latitudes with a particular covariance kernel that I managed to estimate or theorize about. Then, of course, with that, I would be able to interpolate some mean plus confidence intervals. And again, this would be a marginal, let's say, prediction with my covariance. But, well, we may think that, okay, temperature and humidity are related in the sense that, for instance, we can observe here in the data samples a sort of behavior in which the higher the latitude, the lower temperature, and the lower the humidity. That may be attributed, let's say, to a mean function, or maybe we can think and craft some theory in which we understand that temperature and humidity have some statistical correlation. So maybe I can craft some cross covariance between temperature at a position and humidity at another position with some covariance functions k, th, x1, x2. Then, well, if I can put forward an expression for that correlation, be it from a theoretical model, more on that in a minute, be it from an estimation based on prior data analysis, well, then maybe I can use that correlation to improve my predictions, because temperature samples will help me in improving humidity estimations in intermediate points, and vice versa. Humidity samples may help me improve my temperature estimation in points in which I have great temperature uncertainty. Indeed, we will simulate that in subsequent videos. But okay, the motivational idea is here. I can study two signals in a marginal, separate way, devising some marginal prior of the temperature and marginal prior of the humidity and do estimation, interpolation, kriging or whatever in them, or if I have some model of the interrelationship, maybe for instance I may theorize that there is a common component that explains 80% of the variability, let's say, or whatever, then if I can theorize that, or I can estimate that from data, then I can use that correlation to improve my predictions. Then way to do it is, of course, estimating these KT and KH autocovariance kernels and this cross kernel, whatever it is. We'll put some examples later on of the cross relation, which will be based, in common components or whatever. Well, this is one way of finding two output Gaussian processes. From a formal point of view, then, I may assume that I have an object, multi-output stochastic process, whose realizations are random functions, in which my input would be the latitude, and my output would be temperature, humidity pairs. But, well, okay, there is not much difference between two output Gaussian process and single output Gaussian process. There are no multi-output Gaussian processes because I can consider them just being functions of two inputs. One thing will be the latitude and another thing will be an index in which, well, one will be temperature and two will be associated to humidity measurements or simulations. So, from a formal point of view, two output Gaussian processes do not really exist as a separate entity from one output ones, and the only thing that will be worth studying will be the possible correlation between these two outputs or the possible correlation between the functions with input index 1 and functions with input index 2. So, as I will digress in next video, there is no formal difference between two output stochastic processes and one output stochastic processes. But okay, from a conceptual intuitive understanding of this, well, this temperature, humidity and their correlation can give me some insights into studying a particular application. Good. Then now I will discuss a second way of generating this two output Gaussian process, which will be of much more interest for a formal mathematics, physics thinking, in the sense that, well, another way of thinking on random variables is stochastic differential equations, in which, for instance, I may have a mass moving subject to random accelerations, Brownian motion and the like, well, I may have a differential equation saying that the derivative of some position is a velocity, and the derivative of the velocity is 1 over mass times a random force that will be a white noise with, let's say, power spectral density 5 at every frequency. Of course, this is not the formally correct way of writing stochastic differential equations. The dt cannot be in the denominator and whatever. We need the derivative of Brownian motion, blah, blah, blah. But we are not in that level of formality. We are just thinking in engineering terms, okay, a mass moving due to the effect of random forces. In that case, the random force will produce a given velocity, which in fact will be a Wiener process, the integral of a white noise, and the position will be something smoother, which is called, of course, the integrated Wiener process, the double integral of a white noise, but okay, in engineering terms are velocity and positions. Well, the issue is that these two time series, let's say, are not statistically independent. Position now depends on the speeds in the past, or vice versa. The speed now depends on the difference in positions, a small time increment before now and a small time increment after now, let's say. So these two sketches in green and blue are not statistically independent stochastic processes, so there is a correlation between them, and indeed that's the idea. If I have a physical model with differential equations or partial differential equations in which there are some noisy inputs, then I can compute these temperature and humidity variance and covariance and correlations and whatever from the solutions of the stochastic differential equations, be it exact solutions with exponential of matrices if they are linear, be it, via simulation, particle filters, or whatever, Monte Carlo simulation. The thing is that this thing can arise from the study of physical models with ordinary differential equations or partial differential equations. We will not delve into modeling in the subsequent videos. We will just use a descriptive analysis. These covariances come from God, and I just use them for predictions, but, the actual way in which these covariances come are in most cases from a set of differential equations between those variables. Then this kind of position and velocity is one of the ways of getting, correlated functions, correlated random processes. And this is the second example I was considering here. So we can have, let's say, a climate or whatever thing in which I measure two variables in a set of locations, and I get samples of two correlated functions, let's say. In fact, if temperature and humidity are collected at the same points in the methodological stations, then this data set is called isotopic. And if I have temperature readings at some locations and humidity readings at other locations, then those data are called heterotropic. But okay, the underlying math is the same, so don't worry, but just if you hear these words, you know what they are. And the other more interesting approach is crafting these correlations via differential equations, either ordinary ones or partial differential equations, or let's say in signal processing, in which I have a signal f1 of t, then it gets through some filter transfer function, and I get a filtered signal, so there is some statistical correlation between f1 and f2. They are not independent, and in fact, filter basically removes some frequency components from f1 in f2, and explaining all of that is the interesting thing for a formal mathematical study of these stochastic processes. For instance, this plot comes from other materials in the collection in which these red things are position measurements, measurement 1 and position measurement 2. The green dashed line is the mean position extrapolated, or interpolated in between with a given, covariance and whatever. And the blue thing is the mean velocity estimate, and the solid green are the velocity confidence interval, two standard deviations. So given that velocity is the time derivative of position, then with suitable statistical manipulations, we can get the mean and covariance of the velocity from position measurements. And of course, we intuitively expect that in here, in the center point between the two position measurements, is where our velocity estimate is more accurate, our confidence interval is narrower, and my velocity estimate in here will be very close to, let's say, the difference in position divided by difference in time, in the sense that, okay, in this plot, difference in positions is of 1 meter and difference in time is 2 seconds, so the velocity estimate is 0.5 meters per second. Then, with suitable stochastic process theory, we can give a formal treatment of the velocity estimation obtained from finite difference approximations. So given some statistical properties of the exciting acceleration, we can give not only the mean 0.5 meters per second, but a confidence interval and the mean and other points of our velocity estimation. But well, this is only a motivational video for you to think on, wow, these are interesting things. So we will summarize and conclude. We have found some examples on why I can find two functions of time, functions of latitude, or whatever, which are not independent. They are not independent because they have some differential equations relating them, such as these positions and velocities. Here we have the differential equations, very famous ones. Or maybe we can have some descriptive representation in which, based on differential equations or based on whatever data samples from past observations, I get these covariance kernels temperature and humidity, marginal one, let's say, and some covariance between the functions, and then I can study these covariances to make predictions on how things will behave, and using humidity measurements to improve my temperature estimates and vice versa. We will do that in subsequent videos. So we will finish here with these examples, description, and motivation on why would I need to think on multi-output stochastic processes. So we stop here. Thanks for watching.